Hello, we're here today to talk about a literal series of unfortunate events, which are a set of major extinction events that occurred around the end of the Paleozoic. So we've got the end Serpicovian one. So this is going to end the Mississippian. That's number one. At the start of the Pennsylvanian, where we get really cold all of a sudden, we go from hot to cold. We're going to have the Capitanian one. So this is going to be sort of midway through the Permian. We're going to have the Permian Triassic one. That's the big one. These are ranked by the percent of marine entire genera, including all their species, that go extinct. So yikes on that one. 65% of everything is extinct at the genus level. And then just after we get across into the Mesozoic, there's another one. This is sort of midway through the Triassic. It's called the Carnian Pluvial Event. And we'll get to that. Yeah. But we got these four things happening. Boom, 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 boom. Fairly close in geological time. And if you put these together, this is by far the worst span for life on this planet. Thankfully, some stuff made it through, but a lot of stuff did not make it through. So let's talk about this series of unfortunate events. And we have a little graphic above. The sun shines down, the little sunbeams come into Earth. They're going to turn photons into heat energy, basically. That heat energy is going to be trapped in large part by water vapor in the atmosphere. There's nothing we can do with that because we need water on Earth, so water vapor is going to be there. But also stuff like methane that's in the atmosphere and CO2 that's in the atmosphere. Those are going to be really good at trapping. Those are the things that we can potentially control. And so when we have lots of volcanoes that release lots of methane, for example, and CO2, that's going to act as a lovely little shield. So the photons are going to come in, they're going to crash into various molecules in the air or on the Earth. They're going to radiate out as heat energy, whereas they used to be light energy. And that is going to get trapped by these great little heat absorbing chemicals that are now filling up the atmosphere. And so the world is going to warm up. Things are going to get hot. It's about to get hot in here. All right, so let us look. Here's the first event. So this is at the end of the Mississippian, and this is kind of a gradual cooling down, rather. The Mississippian's a fairly warm time coming into the Pennsylvanian. We're going to a fairly cold time. And so what we see is not so much an extinction as an extirpation, Extirpated, which means that things that were living in an area are no longer living in the area. Other things are coming in and taking over. So it's not necessarily that you're driven to death, it's that you're driven out and other things are coming in. Pardon me. And there's some extinction here right at the transition, but for the most part, you're just having things that are getting pushed around. And so what you're getting is a retreat. So all the things that were living in nice cold waters at the poles move toward the equator, which tells us that the world got colder. And there's a bunch of other geochemical ways to also tell that the world got colder, but all of those do agree. So the world is getting colder. So things that used to like it in the cold in, let's say, where Canada is now, all of a sudden can't survive because it's too cold. And so they migrate toward the tropics, which are now cold enough that they are like what the Arctic area was like a few years ago. Yeah, that's global cooling. Yeah, and that's not really any better than global warming. And you get sort of a crowding and a piling up around the equator of all different things because it's the one place on Earth where it is actually warm enough to survive. Yikes. Yeah. Around this time, about halfway in between these, we have an event. And this is the Carboniferous Rainforest Collapse event. We still don't know exactly what happened here, but there were big rainforests that were all around the tropical areas. And Texas was right on the equator during this time. And so, this is one of the areas, this is where a lot of the petrochemicals that at least used to make Texas rich come from. And so what you'll see here is right about there, around the end of the Devonian, beginning of the Masurian, or end of the Muscovian, beginning of the Casimovian, this sort of transitional period is where we find that it's not an extinction of the major types of trees, but the major types of trees are no longer able to live in the areas where they used to live because they're getting pushed out. Because basically the temperature of the globe is changing. Also, around this time, you start to see these cycles. These are those big cyclothems. And so you'll get coal, which is deposited in the swamps. And then you get limestone over the top of the coal because the oceans have risen, because the polar ice caps have melted, and they've flooded all these swamps with salt water and buried them under accumulating rock. And then you'll get the ice caps refreezing and the water dropping back down again. You'll get another coal layer forming as we get back to the shallowest layer. And so, yeah, there are these little sequential coal and limestone. And it's not just coal. It's also natural gas. It's also the oil is down there. And these limestone caps, they're actually called cap carbonates. These are the things that they're going to drill through because these are going to keep stuff like natural gas from just escaping into the atmosphere. They're going to keep it locked under there. And so you drill through those and you pump water or something down into there, and that will then drive up all the lighter stuff, and that's how you get oil out of the ground. Yeah, there you go. So what's happening during this time? We go from vegetation like rainforest conifer type things being displaced. They were over here. They're going to have to move to over in this area, from these swamps to these other swamps. So they're moving to higher ground essentially, which is probably reflecting a temperature change. And we're not sure what else is going on there. But there are some great fossil forests. This is talking about one around Peoria, Illinois, that's from this time. There are fossil forests from central Texas from around this time with great big fossil trees. And then right at the end of the Devonian, those things disappear and they do not come back to this part of Texas. Yeah. So you can go out, you can collect from those areas, you can see it happening right in front of you. This is showing the effect on one particular group of brachiopods, because when temperature is changing and you're living in river deltas, as these brachiopods were, then the river delta is going to be supplied from the land. And so if everything dies on the land, then all of a sudden there's going to be no more nutrients coming down the river. Or if something happens to the land, we get a bunch of erosion happening on the land, then you're going to have a flood of nutrients coming down. Plants are going to do really well for a while. Filter feeders that live off those plants are going to do well. And so brachiopods are like a third or fourth level effect downstream from whatever's happening in the climate. But when you get these major peaks of extinction, like you get extinctions here around the middle of the Permian and a big extinction right here, this is still the middle of the Permian, you know that something has really changed on land. And so here's the rainforest collapse. That's accompanied by a pretty big extinction in these brachiopods. The transition from ice house to greenhouse, so when we come out of the Pennsylvania and go into the Permian, when things start heating up steadily and for good, basically, for a long time, and they're not ever going to refreeze those polar ice caps. We're going on a temperature spike, several million year temperature spike. That is also a major extinction point, just because if things heat up faster than little organisms can move, then the little organisms probably die out. And if other things in the environment, in their ecosystems, were depending on them as part of the food chain, now you got a broken food chain. Broken food chain means nobody at the top of the chain gets food, and so that means extinctions in your predators, in your filter feeders, in your animals. Yeah, because animals don't make their own food. Plants are the ones that make food. Animals are all to some degree either parasitic or predatory, and predation is another word for parasitism. It's the socially acceptable face of parasitism, I would say. Okay, extreme bad thing number 2. Let's pull it over here a little bit so you can see the 2. Ooh, look at that. This is in the middle of the Permian, and this is in the Capitanian. And look what's happening in those carbon isotopes. Remember, when you ever get a negative delta 13 excursion like that, that is a sign that something very bad has happened, and a lot of your plants are probably dead. Or we also have evidence that there were a ton of volcanoes that are occurring here as continents are splitting up or coming together. This is going to be a time when we get just upwelling from the from under the crust to into the atmosphere, basically. And yeah, that's going to be a major environmental perturbation, and it's going to have a big effect. And if you knock out the bottom of the food chain, the top of the food chain does not have a chance. So this is the second big extinction event. And you can see it here. This is, let's see. This is looking at tetrapods, animals with 4 legs, like us. Our arms count as legs. So we do okay. We're just sort of bumping along in, these are the Mississippian. Really start going in the Pennsylvanian when things are cold. So tetrapods really benefited from this sort of icy cold conditions in the Pennsylvanian. And then you see a sort of a curtailing here as the world really starts to heat up. And the tetrapods, maybe it's because they were more able to move, more able to migrate, but the tetrapods do well. So things like birds would be tetrapods, yeah. And they migrate. I mean, they're not the only things that do. Butterflies migrate as well. They are not tetrapods. They're arthropods. But there you see the tetrapods really taking off and exploring new environments, adapting to different kinds of terrestrial environments, for example. Not just trapped in the oceans or in the swamps. Yeah, so it's part of the story of how we got here. We prospered as a result of several really bad catastrophes that affected a lot of other things more than they affected our ancestors. And I think that's just dumb luck. I mean, I guess you'll take it, right? You can't really go back and not take it. But still, yeah, it doesn't mean that the next extinction is going to favor us necessarily. Yeah, we will see. And so this is the beautiful little splash graphic from this paper. And so they're showing that during the third major event, so this is at the end of the Permian and the start of the Triassic, so it's the Paleozoic Mesozoic transition. This is the Great Dying, the biggest extinction. And they're showing, where do we get the most warming? Well, we get the most warming at the poles. Where do we get the most oxygen loss? We get the most oxygen loss in particular in areas around the tropics. When the temperature goes up, dissolved oxygen in the water goes way down. And there may be a combination of geologic and biologic factors that lead to this, sort of differences in CO2 capture organisms, which are going to be things like algae and cyanobacteria. But anyway, what happens is that, yeah, you get a ton of extinction here, particularly near the poles. In the tropics, you're going to have some things surviving, thank goodness. But yeah, the poles are really going to heat up, and the poles are really going to go anoxic. And so that's where we're just going to get wiping out of many of these Paleozoic organisms, which makes way for the Mesozoic organisms to take over, but they are just the survivors. They're the dregs of the Paleozoic that just happen to make it over the line. Now, it's not temperature per se. It is the rate of temperature change. So here is a plot, and as temperature goes up, you're going to be higher on this axis. So you can see from low temperature to high temperature over here. As the rate of temperature in degrees per million years really heats up, and so yeah, like 100 degrees per million years, that is a horrendously high rate of temperature. Now, in comparison, they're saying that we may do a full degree in 100 years, which would be like 10 degrees in 1,000 years, which would be like, yeah, way too many degrees in a million years. And so we're talking about if the current warming trend continues, we're talking about an extinction that's somewhere out over here. So the times when rate of temperature increase is really high and temperature goes up to a really high point, those are the big five extinctions, and they have them actually marked on here. There are other times when the temperature has been hot, but it heated up gradually. The rate was slow, and so that did not result in a major extinction. But every time the rate has gone up in a hurry, very steeply, that has resulted in a major extinction. So this is a not great paper in terms of the future, but this is like an explanation for so many of those major extinction events. KPG, this is the Cretaceous Paleogene. This is the dinosaurs eating it. This is the Permian Triassic extinction, Triassic to Jurassic. This is one is in the middle of the Devonian period, and yeah, there's a big extinction there. There's a big rise, a big sort of greenhouse rise, really rapidly. And coming out of the Ordovician, toward the end of that, the Earth was very cold, might have even had great big glaciation covering most of the Earth, and then we get skyrocketing temperatures and a giant die-off. Yeah, so super. All right. And so what they're doing is they're modeling based on geological sampling. So they're like, okay, this is what happened in the past. Let's see if we can reconstruct what the oxygenation levels were like, because the amount of oxygen is going to be reflected in the types of minerals that you form. When there's more oxygen around, you'll form more oxygen-rich minerals in the seafloor there. It's just it's a nice little proxy marker. And so they're showing at different depths. This is roughly how much oxygen you would expect to have in there, or rather temperature increase. And so showing the greatest temperature increase. So there might still be a little bit of snow falling in the very north and the very south, but right next to that in the Arctic and Antarctic, that's where you're going to get a huge temperature increase, like 15, 20 degrees of increase. And that spells almost certain doom for the animals that are going to be living there. It's going to be a little more stable at the equator, although there's also going to be big changes there. That's going to come with, and here they're showing the continents and relative oxygenation, a big drop in oxygenation, dissolved oxygen in most of the Earth. So oxygen is going to go way down over all of this ocean. And so most of the deep ocean is going to be completely uninhabitable. The inhabitable parts are going to be in this little tiny sea, and this little tiny sea is going to get stirred up a lot because when the continents are about to break apart and like South America and Africa go their separate ways, there's going to be major volcanic activity in this area, and it is not going to be good. Here we're showing the anoxia on the seafloor. And so we're going to go from, roughly 0% at the end of the Permian to roughly 50% of the ocean being completely anoxic and basically off limits to most life as we know it once we are into the Triassic. This is a major cause of the extinction. Habitat with reasonable amounts of oxygen dissolved into the water disappear over about half of the globe. Yeah. And yeah, that would cause a pretty big extinction, don't you think? Yeah. Yeah, I'll bet. So this is plotting different animals that lived around that time, different sorts of arthropods and chordates and cnidarians and mollusks, and plotting their tolerance for hypoxia based on what we know about extant organisms. And so they're saying, okay, this is what living creatures are able to tolerate, the sort of range they're able to tolerate, and this is how much of the ocean would be available to them. So if they're super tolerant, basically all the ocean is going to be fine for them. If they are very intolerant, like they need very high amounts of oxygen, then there are only going to be little tiny parts, maybe 10% of the ocean is the only part where they can exist. And if you get this change in the hypoxic area, the area with low oxygen that they have modeled across the globe at the End-Permian extinction times, this is what happens. For creatures that are out here, you would expect approximately a 100% loss of habitat. 100% equals there's nowhere to go. Guaranteed extinction. The depth at which you used to live is now no longer able to have enough oxygen in it to support you being able to effectively breathe. Yeah. And even for the things that are, more tolerant or are, happier to live closer to shore, these in the higher oxygen environments, these things are really going to suffer as well. This is the change. At least in this particular paper, which is linked a little bit earlier, they are modeling that this hypoxic change, driven by the change in temperature, is going to be one of the major things that got organisms. And this is going to collapse the ecosystem across the ocean. Things on land will do a little better, but still pretty badly, still mostly go extinct. And the oceans are just going to get wiped out. And the oceans are the cradle of life. This is where everything starts to evolve. And so there's just a pause in things that exist and in development of new things across the oceans. So here is our the red dots are what we see in the fossil record. It matches fairly well with what they are modeling over here for extinction events. Same here. They're saying, okay, if we lost this much oxygen, this is how much extinction we should predict. And that is a very good match for what we see in the actual fossil record in terms of extinction. So it's not great, but geology does tell us history in a way, and it shows us what happens when there are big temperature changes on a global scale on the planet. Yeah. So no politics here, just geology. Just geology. Thanks. So that's event number 3. That's the big one that really knocked everything else out. And then the survivors just crawl their way back into the world. Things cool down a bit from their End-Permian peak. And then all of a sudden, you've got the Carnian pluvial episode where we get extreme erosion on land because we think there's extreme precipitation on land. The idea is that this is pretty much nonstop rain lasting for hundreds of thousands to millions of years, and that it basically washes all the topsoil off, most of the organisms that are living in there, and it completely changes the land conditions. So all these land creatures that are laughing at the ocean at the end of the Permian when everything becomes anoxic and they can't breathe, now all of a sudden just get completely washed off the land. All the things that they would have eaten are destroyed. It collapses the plant biota. That then leads to a collapse in the animals that would have fed on the plants or on the animals that fed on the plants. And so, 1, 2, 3, dominoes. Down they fall. So this is just looking at some of the extinction. Here's our big Carnian pluvial event. Here's our drop in C13 as land plants get driven to extinction, most likely. There's no giant volcanoes to explain why we would have an excursion in C13 at this time. And the ones that come out of it end up being the early things that are going to go on to become the reptiles that you know and the dinosaurs. Yeah. So the dinosaurs happen. Mammals, here there are little mammals, happen as a result of everything else that was doing well on land being more or less driven to extinction in the Carnian pluvial event and in the preceding End-Permian Triassic extinction event. So there you go. 4 bad things packed into just a small number of million years, maybe 100 million years, which is a pretty short time in geological terms. And animals suffered, but it shaped the evolution of the animals that came out of it. These are things that maybe wouldn't have developed or could not have survived if there had been more competition from the animals that were already there. So thanks, I guess. Sorry about the extinction. Thanks for the chance for stuff like us to get going. But here again, we came out of that one looking all right. But it's hard to predict who is going to do well and who is going to die out in the next big extinction event. So, Hope we do all right. All right. Thanks a lot. This has been extinctions, particularly the end Paleozoic extinctions.